talking about inverse functions. Two functions are inverses, f and g are said to be inverses if f circle g of x is equal to g circle f of x. By definition, that means f of g of x, and by definition, this means g of f of x. Notice the order doesn't change. G, f, x. G, f, x. F, g, x. F, g, x. And they're equal. Oh, and they have to equal x. Both of these equal x. This should equal x, and that should equal x. They both should equal x. They should both equal one another because they equal x. They both should equal one another and equal x. Not equal, they shouldn't both equal 17. That is the definition of inverse function. F and g are said to be inverse functions if f of g of x equals g of f of x equals x. I'm going to give you two functions, and you're going to decide if they're inverses or not. Inverse functions undo one another. You plug x in, you get x back. You plug 7 in, you get 7 back. F does something to it, and then g undoes it. You plug your number in, f will do its thing on it, and then g will come and undo it. And you'll get back the number you plugged in. So, if I tell you f of x is x squared, or how do you undo squaring something? You take the square root of it. Actually, I don't want to get involved in that. Let's make it cubed. You cube something, how do you get it back? You cube root it. That is, if you had a number in your calculator and you forgot what it was, but it's 7, and you cubed it, and you got 343, and you say, oh, now you forgot it was 7. You forgot what you cubed. And you say, oh my, I didn't mean to cube it, I meant to add 3. Well, what you would do is, you don't start the calculation over. What you would do is you would take the cube root of it, and back would come that number, 7. And then you would add 3, and you'd be back to where you meant to be. Or you'd be where you meant to be. To undo cubing something, you don't start over. You take the cube root of it. So yeah, those are inverses. Those are inverses. Remember, cube root means raised to the third power. So we need to look at f of g of x. It's f of g of x. F of g of x. But that's g of x. Now, what is f? I'm looking here. What does f do to what you put in the brackets? It takes what's in the brackets and it raises it to the third power. So what's f of this? Well, I take what that is, and I raise it to the third power. Remember, when you raise x to powers and into another power, you multiply the powers. 1/3 times 3 is 1. You get x to the 1 or x. So on a roll. We did half of it. Now we have to do g of f of x. But f of x is x cubed. It tells me right here. So it's g of x cubed. Now what is the job of g? What does g do to what's in the bracket? Well, it takes what's in the bracket and it raises it to 1/3. Okay, I don't care what's in the bracket. I take what's in the bracket and I raise it to the third. 3 times the third is the same as the third times 3. It's 1. And x to the 1 is x. So they're both x's. So we conclude f and g are inverses. F and g are inverses. Not every function has an inverse, but f and g did. If the inverse of f is g, and the inverse of g is f, those functions are inverses. Suppose you were told that f of x is 5x plus 1. Now, how would you find the inverse? Well, you put a number and you calculate x. And then you multiplied it by 5 and you got 5x. I'm trying to build this up. Well, I have 5x. Now I'll add 1. That gives me 5x plus 1. Well, how would you get back the inverse? Call this big X. That's what's in your calculator now. You took a number in your calculator, you multiplied it by 5, and you added 1. Well, if you take away the 1, if you have 5x plus 1, and you take away the 1, you'll have 5x. And then if you divide by 5, you get back the number you started with. I'm going to undo what I did. Undo adding 1, take away 1. So you have x, and you take away 1, you have x minus 1. To undo multiplying by 5, I divide by 5. So I take this, and I divide by 5. That's the inverse. Let's call it g. I know these are inverses. So not only are we going to imagine the problem asks giving those two functions to show that they're inverses. But we did a little bit more. We actually found the inverse. Okay, so make believe we didn't find it. The problem gives you f and g, and they say show that they're inverses. Let me write g a little bit higher. X minus 1 over 5. Now just for the record, if you took x, took a number, and then you took 1 away from it, and you divided it by 5, call that result big X. If you multiplied by 5, then you have x minus 1. Oh, I'll add 1. Remember, x minus 1 plus 1 is just x. That's the inverse of g. It's exactly f. It's working like the charm. Your textbook would tell you to interchange x and y and then solve for y again, and that would be your inverse. Problem with that is, yes, it works, but in my opinion, there's no understanding as to why it works or what an inverse means. Okay, let us calculate f for g of x. G of x is x minus 1 over 5. So what does f do to x minus 1 over 5? What does f do to anything that's in the bracket, like x? It multiplies it by 5 and then adds 1. Okay, I'm going to take what's in the bracket. I'm going to denote I'm multiplying it by 5 and adding 1. Well, the 5's cancel and you get x minus 1 plus 1. Oh my, you get x back. You get back what you started with. Okay, let's look at g of f of x. It's g of f of x. F of x happens to be 5x plus 1. What does g do to this? G does to that the same as what g does to good old x. It takes away 1 and it divides by 5. Okay? I'll take away 1. At least I'll denote it, and I'll divide by 5. Well, the 1's cancel. 5x plus 1 minus 1 is just 5x. Oh my, when you divide it by 5, you get back x. F and g are inverses. That is how you would show If you're given two functions f and g, convince me that they're inverses, show that you get x in both of those trials. If you don't get x in one or both of them, they're not inverses of one another. They're not inverses of one another. Now, how might you graph the inverse of a function? For example, if you have y is equal to 2x, the inverse, well, how you undo multiplying by 2 is you divide by 2. Now, if you were to graph these, here's the line y equals x, and here is the line y equals 2x, this is y equals 2x, and in red, here is the line y equals a half x. Or x over 2. The two lines are mirror image across the line y equals x. Here is the line y equals x. If you drew the blue line on a piece of paper and you in heavy ink, very heavy ink, and you folded it along the line y equals x, that ink would give you y equals x over 2, the inverse. It's the mirror image. Take a point on the line, go at a right angle to the line y equals x, and however far you went, go the same distance more, you'll find a point on the inverse. Here is the line y equals x. If this is f of x, then the inverse would be the mirror image. And the inverse is denoted that way. F inverse. They're mirror images across the line y equals x. Here is the line y equals x. Here is some function. Call this function f of x. The inverse would just be that. That would be the inverse. It's just the mirror image. If this distance is 1 inch, right angle, then that distance at a right angle must be 1 inch. If one line crosses, if one curve crosses the line y equals x, well then they both do. They both cross. If this distance is ½ inch, then that distance should be ½ inch. Both right angles with the line y equals x. This line is 5.1 inches, then that distance should be 5.1 inches. I'm drawing that a little bit better, but oh well. If this is -7 on the x-axis, and that's -7 on the y-axis. If this is 2 on the y-axis, that should be -2 on the x-axis. They're mirror images. +2, excuse me. They're a mirror image, x and y. So, if you're asked to draw a function and its inverse, put all your energy into getting the first graph correct, plot points, take derivatives, whatever. Get it correct. And then the invert is just the mirror image. If I tell you f of x contains (0, 2), -3, 4, and the point 1, 3. Let's not go out to 8. 1, 3. Then their inverse will contain, well, just interchange x and y. It'll contain 2, 0, and 4, -3, and 3, 1. Let's graph this. Zero, 2 is right here. Well, if you reflect this across the y-axis, well then you're going to get this point. So, yeah, they do live up to what we've been saying. If f of x contains -3, 4, 1, 2, 3, -3, 4. If it contains that point, well, f inverse is going to contain 4, -3. It's going to contain that point. The same distance from the line. When I go at a right angle, it's the same distance. 1, 3. Excuse me. 1, 3. 1, 3. 1, 3 is right here. 3, 1 is right here. Right here. They're mirror images. Right angle. Right angle. Of course, I did 31. Alright, so let us plot that point correctly. It's 3, 1, which is in the first quadrant, sorry. It's right here, 3, 1. And they're the same distance away. Each point is the same distance away from the dotted line. Remember, given any line and a point, by the distance, we don't mean that distance between the line and the point, or this distance. We mean the distance that meet at a right angle. So we have the inverses. If you just interchange x and y, you get the inverse. And if you wanted to bother proving it, well, I won't, but if you wanted to bother proving it, here is an arbitrary point xy, and here is the line y = x. Well, you need to do a few things. you need to determine the equation of that line. But that, well, let's not call it xy, let's call it AB. You need to determine the equation of this line. But that's not so bad to do. So if you know this line is y equals x, 1x. So the slope of this line will be the reciprocal, the negative reciprocal of negative 1, the negative reciprocal of 1, which is negative 1. So I know the slope of this line, I know the slope of that line, and I know a point. I can find the equation of the line. Okay, now you find the equation of the line, you need to find out where it intersects, where the two lines cross. Okay, now you have where the two lines cross. Now you have to find that distance. Now you have to find that distance. Okay. One more thing. Now what you have to do is pick an arbitrary point over here. And you know this point now. And you want this distance to equal the same as the first distance. And you will find out that this point is BA. In fact, let's assume it's BA. Find the distance from the point of intersection to BA. And you will see that it's the same as the point of intersection to AB is. They'll both be the same length. Okay, if you reflect the point AB across the line y equals x, you will get B comma A. You interchange the x and the y value. That is why if you have the point 3, 3, which lies on the line y equals x, because y equals x, if you interchange them, you get back the same point. Both of those points will lie on f of x and the inverse of f of x. Suppose you're told you're given f of x is equal to x over 2, and g of x is equal to x plus 1. Well, to undo dividing by 2, you multiply by 2. That is the inverse of f. Okay, so let me hold up a moment. You're given that, and you're asked to find f inverse circle g inverse of 7. That's what you're asked to find. Find that if f of x equals x over 2 and g of x equals x plus 1. Well, before you can calculate this, you need to know f inverse and g inverse. So below this line is where the problem is going. We found f inverse and g inverse. To undo adding 1, you take away 1. You need to be able to see that. Okay, so now f inverse circle g inverse of 7. By definition, this means f inverse of g inverse of 7. Now, these inverses, f inverse, g inverse, is just a name for a function. It's just a name. I mean, if you don't like g inverse, you just put h. But you better tell everyone, hey, h equals g inverse. And then nobody can say, what is this person doing? What is h? You should tell everyone. You should write down. Let h equals g inverse. So let h of x equals g inverse of x. Then you don't have to write down g inverse if it's going to bother you. If you did that enough, it'll start bothering you that you're not writing down g inverse. So we need to first find G inverse of 7. So this is F inverse of whatever G inverse of 7 is. X is 7. 7 minus 1 is 6. If I plug 7 in there, then I have to plug 7 in the right side. 7 minus 1 is 6. What does G inverse do to what's in there? It takes away 1. What's in here? In the bracket, 7. I take away 1. Now, what does F inverse do? It doubles. All right, I'll double 6. Problem done. Need to be able to say in words what the function does. If you can say it in words, you're okay. What if you were asked to find something different? Same two functions f and g, but you're asked to find something different. You are asked to find something different. You are asked to find G inverse circle F inverse of 4. You are asked to find this. So, we have the two inverses. They didn't change. They did not change. I hope that is very clear. They did not change. Okay, so you have G inverse circle F inverse of 4. This is equal to G inverse of F inverse of 4. What does F inverse do to what's in the brackets? It doubles it. It double what's in the brackets. I double 4, I get 8. Now what does G inverse do to what's in the bracket? It takes away 1. So I get 7. Now, let's talk about, not every function has an inverse. Let's talk about that. Suppose I tell you that f of x is x squared and g of x is the square root of x. Let us compute f circle g of x. Let's see if they're inverses. This is f of g of x. And g of x, well, that's given. It's square root of x. So it's f of square root of x. Now, what does f do to what's in the brackets? It squares it. Well, if you square the square root of x, you get x. You get x. So it looks like maybe they're going to be inverses. But if you go the other way, maybe you won't get x. F of x is x squared. So g is x squared. And the job of g, it takes what's in the brackets and it puts that symbol above it. It takes the square root of what's in the brackets. The problem is the square root of x squared, well, it's not x. You may say, well, what are you talking about? The square root of x squared is x. Well, if I plug 4 in, then I get the square root of 16, which is 4. Square root of 16, which is 4. That is, I did get what was in the brackets. But what if I take the square root of negative 5 squared? That is, I take the square root of 25. I get back 5. That is not what's in the brackets. 4 equals what's in the brackets, but 5 does not equal what's in the brackets. In fact, I'm getting back the absolute value of what's in the brackets. The absolute value of 4 is 4. The absolute value of negative 5 is 5. The absolute value of x is not x. The absolute value of negative 3, for example, does not equal negative 3. So I'm not getting x back in both of them. Okay, I'm not getting x back in both of them. Them being f of g of x and g of f of x. I'm not always getting x back. One moment, please. This here, it gave me back x. But when I reversed it, I did not get back x. So, f and g are not inverses. That means if you square a number in your calculator, you can't necessarily get back your answer. If I took the number that was in my calculator, but I forget what it was, I take a number and I square it. Everyone else knows it's negative 7 except your next door neighbor. That's the person who typed it in the calculator. All they get back, so they forgot what they squared. They got back 40, they get 49. And you say, oh my, I didn't mean to square, I meant to cube, or I meant to multiply by 98. I accidentally hit the square button. Well, you may say, not a problem. Take the number that's in your calculator and take the square root of it. Problem is you may not get back the right answer. Of course, if you started with 7, you got 49. You forgot 7. Who remembers what was in the calculator before the last step? I certainly don't. I look at my calculator and I see 49. I don't remember 7. But maybe I remember I squared. So if I take the square root, I do get back the number. That is, you may not get back the right number. The right number, in this case, was negative 7. The right number in the second case was 7. You may not get back the right answer. Okay? And the reason is, if you look at the graph of x squared, if you go to 49, it equals 49 2 times. It equals 49 when x is negative 7, and the y value equals 49 when x is plus 7. It failed what's called the horizontal line test. I can draw a horizontal line and it crosses the graph in 2 places. This function does not have an inverse. This horizontal line crosses the graph in 2 places. Other than the line I just drew, this here is the graph, what's in red. This horizontal line crosses the graph in 2 places. You can't retrieve back the number that you originally started with. If you have this function right here, let me draw the graph in red. If you have that function right there, here is your x-axis, right here is your y-axis. You're not going to be able to easily retrieve back a number. For example, if you look down at your calculator and it says 17, and you did something to it, you won't be able to retrieve the number that you did something to. You had a number in your calculator, you did something to it, you squared it and added 9 and took away 3, and then took the log of it and then raised it to the 17th power. You did things to it. This is the graph of what you did. You took what was in the brackets and you in the calculator you squared it and you added 7 and then you took log of that and then you raised it to the 13th power. Let's make believe that that's the graph of log of x squared plus 7 all raised to the 13th power. Let's just make believe that's the graph. Well, it doesn't matter. Whatever you did, you can always draw a graph of what you did. Okay. But now can you retrieve back a number? Now this is silliness, I'm just going to erase it. You did something, and that something has a function associated with it. Now the question is, can I erase my board? That's the question. But the other question is, can we retrieve back the information? Well, sometimes maybe. For example, if you got back this number, assuming this line is perfectly straight, yeah, you can retrieve back that x value. If you got 17, you can retrieve the 3 back. But you know what? If you got 11, you are in deep trouble. Because 11, you can get 11 4 different times. You can get 11 by plugging in -12, by plugging in -2, by plugging in -1/2, and by plugging in 4, for example. So you will not be able to retrieve the x value. Fine, you'll know it was either -12 or -2 or -1/2 or 4. You'll know that. Fine. But you won't be able to get it back to an exact answer. You will not know the exact number that you plugged in. And why not? Because it didn't pass the horizontal line test. Is this here a graph of a function? The answer is no. Excuse me, a function that has an inverse. The answer is no. To pass the vertical line test, no vertical line, horizontal line. To pass the horizontal line test, no horizontal line can cross the graph in more than one place. To pass the horizontal line test, and that is for a function to have an inverse, they must pass the horizontal line test. That is, no matter which horizontal line you draw, it cannot cross the graph in more than one place. What I am drawing in red, and I mean what I'm drawing in red, not part of what I drew or anything. More than I drew, no. Exactly what you see in red is the graph. And I didn't mean to draw this function, excuse me. This function here. Is this, let's put it in red. Is this the graph of a function that has an inverse? Is this the graph of a function that has an inverse? And anything and everything that you see in red is part of the graph. You want to see the axes? Fine, I'll draw axes. I'll put them kind of out of the way. This horizontal line, this is not a graph of a function because that horizontal line crossed in more than one place. It's not, I didn't mean to say that. It's not, this function does not have an inverse because I found the horizontal line that crossed in more than one place. This horizontal line crossed in more than one place. This function does not have an inverse. function only has an inverse if it passes the horizontal line test. That is, no horizontal line crosses in more than one place. So what about this graph? Here's the axes, and I'll draw the graph in a moment. I'll draw it in red. Does this function have an inverse? This is a function. I'll even give it a name. F of x. Does f of x have an inverse? Well, you may say, let's see, this line, horizontal line, crossed in one place. This horizontal line crossed in one place. This horizontal line crossed in one place. But you know what? That horizontal line crossed in two places. Anything in red was part of the graph. F of x does not have an inverse. There's only one horizontal line that crossed the graph in more than one place. And it was this line right there. This line crosses the graph in more than one place. It crossed it right there, and it crossed it right there. Okay. Now, want to change this graph ever so slightly. Ever so slightly. That open circle means right at that point, there is no point. There is no point there. Everything you see in red is part of the graph. That circle, there's no point there. This is the graph of a function. Because any horizontal line I draw, including this one, it only crosses in one place. It only crossed there. This f of x does have an inverse. Of course, if I went and put another point right there and not remove this point, it would not be a function. It would not be a function. If any horizontal line crosses the graph in more than one place, it is not a function. If no horizontal line crosses in more than one place. I keep saying function, I mean to say it doesn't have an inverse. If a horizontal line crosses the function in more than one place, that function does not have an inverse. If you can find even one horizontal line that crosses the graph in more than one place, that function does not have an inverse. If, on the other hand, you or nobody can find a horizontal line that crosses the graph in more than one place, then that function, that graph, does have an inverse. Now, I keep saying in no more than one place. Let me be clear what I mean. For example, if you have a curve that starts here and finishes there, it doesn't even include that endpoint. This graph, this function does have an inverse. Because this horizontal line crossed the graph nowhere. That's okay. You fail to have an inverse if you cross in more than one place. This horizontal line did not cross the graph. This one did not. This one does in one point. This one does in one point. This one at one point. This one crossed the graph nowhere. Remember, that point isn't there. It's not part of the graph. This line crosses nowhere. No horizontal line will cross the graph in more than one place. So this call it f of x. F of x does have an inverse. F of x does have an inverse. This here is f of x. This is f of x, and it has an inverse. Now, the last thing we're going to talk about is what does it take for a function not to have an inverse? You have a function that's going up, that portion has an inverse because it'll pass the horizontal line test. What happens is that if it continues to go up forever and ever, that means f prime of x is always positive. The slopes of the tangent lines are always positive. Possibly 0 at one point. They're always positive. Then this graph has an inverse. If the slopes are always negative, f prime of x is always less than 0. It's always negative. No matter what horizontal line you draw, it'll never cross the graph in more than one place. Same thing for over here. It'll never cross in more than one place. Okay. When will it cross in more than one place? Well, when it goes up and then comes down. To the left of this line, the derivatives are positive. To the left of that line I drew, the derivatives are negative. They cross. A horizontal line can cross in more than two places. So if you can show, so this function, sometimes the derivative is positive, sometimes it's negative. From here on, it can go positive again. And then from here on, it can go negative, etc. That function will not have an inverse. If the derivative, here it is, listen. If the derivative is always positive or always negative, then the function will have an inverse. If f prime of x is greater than 0, that's the symbol for all. That means for all. For all x, or f prime of x is less than 0, for all x, then not f prime, but f of x has an inverse. So that's a test to see if a function has an inverse. And if you're given the graph, just picture every horizontal line. If you see that it crosses in more than one place, if you can see a horizontal line that will cross in more than one place, then this graph does not have an inverse. So, show that this graph, or this function, has an inverse. Show that this graph has an inverse. Show that f of x has an inverse. Well, you can graph it, but that's not really a proof. So, this means for all. So what you do is you take the derivative and you get x squared minus 1. Let's make it plus x, excuse me. Well, x squared, if you square, I like to think of there being three types of numbers. Negative numbers and numbers 0 and positive numbers. If you square a negative number, you get positive. If you square a positive number, you get positive. If you square 0, you get positive. So when you square a number, the least you'll get is 0. This is 0 or more. Well, if you add 1, it's going to be 1 or more. This is greater than 0 for all x. So f of x. Oh, actually, I did have it. I just wrote the derivative down wrong. So f of x has an inverse. If the derivative is always positive or always negative, then it will have an inverse. You take the derivative of a function and you show that it's always positive. And you say, yep, it has an inverse. Or you show that it's always negative and you say, yep, it has an inverse. Or you show that it's both, sometimes it's positive and sometimes it's negative. Then it won't have an inverse. Suppose I tell you f of x is equal to x minus 4 squared, but I tell you that x is greater than 4, greater than or equal to 4. Does this function have an inverse? Well, let's see. The derivative will be, it's a function to a power, so you keep the function the same. Bring down the power, make the new power 1 less, take the derivative of what's in there, which is 1. So you get 2 times x minus 4 to the 1 is just x minus 4, and you don't have to bother multiplying by 1. But remember, x is greater than or equal to 4. This will never be negative. So f prime of x is greater than or equal to 0 for all x at least 4. So f of x has an inverse. To direct it, x minus 4 squared looks like this. And that function doesn't have an inverse because it's going to fail the horizontal line path. But I'm only taking into account the x values that are bigger than 4, bigger than or equal to 4. It's just this. This portion of the graph, x minus 4 squared, has a function. No matter which horizontal line I draw, it only crosses it in one place, or no places. It never crosses in more than one place. So that is the graph of a function that has an inverse. Okay, that finishes this section on inverses.